Okay, so today's lesson is on a concept called percent yield. We've actually briefly used this a little earlier on in this course. We did a lab in person using malachite, and I had you calculate basically the percentage of which the malachite we actually obtained from the reaction, or rather the product of the malachite reaction that was actually obtained in the reaction as a percentage of what we expected with a stoichiometric calculation. Anyway, let's get going. So if you can believe it, this is actually the last outcome of Chemistry 20, percent yield. So after today, it's just pretty much a review from here on out. For percent yield, basically, this is just calculating what percentage of your predicted amount you actually received. It just expands what we've already been doing. It's no different than what we've been doing. It's just there's an extra little equation for calculating the percentage yield that we received. There's going to be a couple curveball questions I'll throw at you today. And this will be where you'll learn how much was produced if all you were given is the percent yield. Wow, that sentence is a bit of a mess. So in other words, there'll be questions where I'll say your percent yield was 25%. How much was you actually produced, right? Anyway, let's keep going. It'll make more sense when we see it. So again, this is on page 35 in your note package. More often than not, your experiment does not work perfectly, and 100% of the expected amount of products are not obtained from the reaction. Reduced yields may be due to a variety of reasons. One reason could be the reactants may not completely react due to impure reactants or insufficient reaction conditions. When we did that malachite lab, I think some of you had some hot plates that weren't really working so well. So some people who had better hot plates had a more complete reaction than others. Anyway, another reason could be some of the products may be lost during the procedure. For instance, solvent extraction or filtration. So in other words, during some method in the procedure, you might have actually lost some of the products. They would have been removed from the system, whether they stuck to something else or who knows what. They basically just disappeared somehow. So in other words, it's not necessarily that they didn't react to form that, it's just that they ended up being caught to something else. Now, it's also possible to have a greater than 100% yield. This may be due to a variety of issues, and it's not a good thing either. You might have a contaminated product, so unwanted product obtained, and there were some impurities present, or the products may not be completely dried. So in other words, when you measure them, there might actually be some like water or some other stuff in there, right? Anyway, stoichiometric calculations provide us with the expected amount if the reaction worked 100%. If you know the expected amount of product based on stoichiometric calculations, that's what we've been doing this whole unit, and you measure the actual mass of the product formed, you can calculate the percent yield of your experiment. Percentage yield just basically is your obtained value, so the actual mass that you've measured after you did a chemical experiment, divided by the expected value that you got from stoich, right? So in this formula, obtained is the experimental value. In other words, what you actually measured in your experiment, like the real world thing, and expected is the stoichiometric value calculated using your limiting reagent, right? So in other words, using stoichiometry, how much you actually expected, like if I said, oh, how much mass will form, that will be your expected value. Your obtained value is what's actually measured in a lab. All right, we'll do an example here. When 15 grams of CH4 is reacted with an excess of Cl2, according to the reaction, there it is, a total of 29.7 grams of CH3Cl is formed. What is the percent yield of the reaction? Step one, find your expected mass using stoich. So you should always use your stoichiometric principles, so using your balanced chemical equation to figure out, how much your expected mass will be. This mass that the question gave us of CH3Cl is your obtained. In other words, that was your experimental value. That's what was actually measured from this chemical reaction. We want to find what stoichiometry would expect from this, okay? Now, this equation up here, by the looks of it, it is actually balanced already for us. I know there's no coefficients, but if you look at the number of each element in there, you'll see it is a balanced chemical equation. And since it's a balanced chemical equation, we want to take what we know, which is in this case is your mass of CH4, and use it to predict the experimental mass, or rather the expected mass of CH3Cl. The only way to do that, of course, is using your molar amounts, as we always should start with. So let's start with those moles. We know we have 15 grams. Since we want to get moles, we need to use the molar mass of CH4. The molar mass of CH4 is the molar mass of carbon, which is 12.01, plus 4 hydrogens, which is 1.01. And that gives us 16.05 grams per mole. If you set this equal to the number of grams we have, which was 15.0, and divide it by the number of moles, you can, of course, cross multiply and realize that the number of moles you'll have is 0.934579 moles. And again, this represents the number of parts for this, so 1 part. And since that represents just 1 part, we can look at how many parts of CH3Cl we have. And what do you know? It's also 1 part. So that means it's going to be the same for CH3Cl. So we know how much CH3Cl that we have in terms of a molar amount. Now we'll find the molar mass of CH3Cl to find the expected mass. Now the molar mass of CH3Cl, of course, is carbons, so 12.01, plus 3 hydrogens, so 3 times 1.01, plus 1 for chlorine, which is 35.45. Long story short, that's going to be a total molar mass of 50.49 grams per mole. And let's set this equal to X for grams over the number of moles we have, which we calculated already to be 0.934579. Multiply that over to the other side, and you're going to find that X is going to equal to 3 sig digs here, 47.2 grams. So what we just did there was no different than what we've been doing this entire unit. We've just been calculating how much mass of a product we can expect in a chemical equation, right? This, however, what is different this time around is this is representing what we can consider our expected amount. I want you to notice that your expected amount is less than what we actually obtained. So in other words, it wasn't a 100% perfect chemical reaction. We lost some of it somewhere, or maybe not all of it actually reacted. That kind of is irrelevant to what this question is asking, but in part 2, it says using your percent yield calculation and your experimental value described in the question, determine the percent yield. Percent yield is just your obtained, so how much you actually got from your experiment, divided by your expected, which is what Stoich would tell us. And then of course you just times that by 100 to turn it into a percentage. So long story short here, our percent yield is going to equal what we had for an obtained. The question told us was 29.7 grams. That's what the people actually measured in the experiment. Divided by expected, that's what we calculate using Stoich. We found that to be 47.2 grams. And then we just got to times the answer to that by 100. Long story short, the percent yield here is going to equal about 60.4%. So in other words, the amount of CH3Cl, that amount of CH3Cl that was actually formed was only 60.4% of what we would have expected it to be. Okay, so that is what we call our percent yield. Let's do a couple more questions here real quick. What mass of K2CO3 is produced when 1.50 grams of KO2 is reacted with an excess CO2 according to the reaction below, if the reaction has a 76.0% yield? Ooh, okay, so this time around, we actually are given our percent yield first off. Let's kind of just take stock of everything else we have, though. We're looking for what mass of K2CO3 is produced. So this is what we're looking for. Now, since it's asking what's being produced, that we can assume is going to be our obtained. Now, traditionally in the past, we would have said the obtained was the same as the expected because all the other questions we've ever done have just assumed it was a 100% yield. But because we're actually looking at what is produced and we know how much percent yield we have to recognize that that's going to be a little bit different than what our actual expected value would be. Nevertheless, though, we should find our expected amount using Stoich because there's nothing stopping us here from doing that. We know the mass of KO2 that is used. We can use the molar mass of KO2 to find the number of moles of KO2, and then just use our molar amounts using our coefficients to figure out how many moles is going to be expected to be produced. Long story short, let's start with KO2. To find the molar mass of KO2, it's just the molar mass of potassium plus 2 times the mole of oxygen, or the molar mass of oxygen. So that'd be 39.10 plus 2 times 16. And that's going to give you 71.10 grams per mole. That's the molar mass of KO2. Now set this equal to the number of grams of KO2 you have, which was just 1.50 divided by the number of moles. Cross multiply here, and you're going to see that the number of moles of KO2 that we have right now is 0.02 10970464 moles. I kind of went totally off there. I wasn't even looking at the screen. I was looking down at my page. Apologize for that, but you get the idea. That's how many moles of KO2 that we actually are reacting here. And again, that's with an excess of CO2. When you see excess of CO2, that just means you don't care about how much you have. You're using enough CO2 is basically what that means. Now I want you to recognize though, this is according to our balanced chemical equation, this is 4 parts. And we're looking for how much K2CO3 is produced. Well, that's 2 parts, right? A couple different ways you could do this, of course. I think most of you would just agree, since this is 4 parts and we want 2 parts, you can just divide this by 2, because 4 divided by 2 is 2 parts. If you don't see that though, you could also think divide it by 4 to get 1 part, and then times that number by 2 to get 2 parts. Either way you do it though, I'm just going to say divide by 2 just because it's simpler. Either way you do it though, the number of moles of K2CO3 that's going to be produced is N equals 0.0105485,232 moles. And again, that's of your K2CO3. So since we now know the number of moles of K2CO3 that's being produced, we should figure out the mass that would be expected from this. So we'll need to use the molar mass. The molar mass of K2CO3, well, let's do this. It's going to be 2 times molar mass of potassium, so 2 times 39.10, plus 1 carbon, which is 12.01, plus 3 oxygens, which is 3 times 16. That's going to equal a grand total of 138.21 grams per mole. And that's going to equal some number of grams over our number of moles, which is 0.0105485,232 moles. Multiply that over. Super interesting stuff. I totally understand, guys. If you multiply that over, though, you're going to get X is equal to 1.457911 grams. Now, the reason I kept so many digits there is because this is not quite yet our final answer. We're looking for how much is actually obtained. In a previous question, we would have said this is how much is obtained, because we always assumed, oh, everything has a 100% yield and the math we do for stoichiometry is perfect no matter what. No, the reality is it's not. It's a harsh reality, but here we are. We actually only have we actually only have a 76% yield. So that means our percent yield, which is 76%, equals our obtained amount, what we actually will get from an experiment. We'll say that, I'll even just call it obtained, just so we can see it there. You don't even have to give it a variable. Just call it obtained over the actual expected amount that we were going to get. So we knew how much KO2 we were using, and then we were able to turn that into a number of moles and predict how much expected would come out of that. So that's going to be 1.457911 grams. And then, of course, that needs to be times by 100 to turn it into a percentage. Long story short, divide away that 100, you have 0.76 equals obtained over that number. I'm going to be lazy. Multiply by that number on the other side, and you're going to find that your obtained amount is going to equal to 3 sig digs here, 1.11 grams. So long story short, what I'm trying to get at here is, since we're looking for how much is produced, that's looking for that experimental value, the amount that was actually produced during the equation. So in other words, we had to use our percent yield from that, and we use STOIC to figure out the expected. That number that goes down in the bottom for expected value is always, always, always found using STOIC, unless the question just gave it to us, which would be pretty rare. It doesn't really happen very often. But anyway, let's go on. All right, so question 3 here. What mass of CuO is required to make 10 grams of Cu according to the reaction if the reaction has a 58.0% yield? Okay, so Cu, copper, that's actually one of our products here. We're looking to make 10 grams of it. That is what we would consider our obtained. That's what we're obtaining from this. We know the reaction is only 58.0% yield, so that means only about half of it, half of what we are expecting will actually be produced. So maybe what we should do is use our percent yield first, because we know nothing about this CuO. We're trying to find the mass. So it's almost like we're working backwards here. Let's use that percent yield first. So 58.0% equals our obtained, which we know is 10.0, over our expected times by 100. So if we divide away the 100 first, we have 0.58 equals 10.0 over expected. Times by expected, divide by 0.58, and you're going to find that our expected amount that we would get through STOIC is going to equal, there's going to be a lot of digits here, 17.24137931 grams. And that again is of copper. So we are expecting to have that much copper in order to actually produce 10 grams of it. Because again, the reaction only has a 58.0% yield. So that means the actual obtained is 10.0. That's how much expected we'd need here as well. Hopefully I'm talking some sense here. It feels like I'm just jumping all over the place. Anyway, so since this is our expected, that's what we're going to use with stoichiometry. Now by stoichiometry, of course, I always mean that's what we're using with our moles. So what would be really useful here, and this is working very much backwards, but what would be really useful here is if we figured out how many moles this is, and then we use our stoichiometry calculations to figure out how much mass of this we would have needed in the first place. So to figure out our number of moles of this, we can just use our molar mass of copper. The molar mass of copper is just 63.55 grams per mole. So set that equal to the number of grams we have, which is 17.24137931 over the number of moles, which is what we're looking for. Multiply that over, divide by 63.55, and you're going to find that N is equal to 0.2713041591 moles. And the other thing I want to recognize is this is technically, in terms of our chemical equation here, this is representing 3 parts. What we're interested in is how much CuO is produced. But notice CuO right over here also has 3 parts. That was pretty convenient. So this is going to be the same for CuO. So we know this is how many moles of CuO, that's copper oxide, I might as well call it by its real name, copper oxide, that's how many moles we'll have of it. So if we're looking for what mass of that is required, we just need to use the molar mass of CuO. So the molar mass of CuO is the molar mass of copper, which is 63.55, plus the molar mass of oxygen, which is 16. That gives us 79.55 grams per mole. That's the molar mass. Set that equal to some number of grams, which is what we're looking for, over your number of moles, which is 0.2713041591. Multiply that over to the other side, and you're going to find that X is going to equal to 3 sig digs, 21.6 grams of CuO. Boom. So, long story short, explaining this question one last time, we knew that we wanted to make 10 grams of Cu. So that is how much we actually want to obtain. The reaction is by no means perfect. It only has a 58.0% yield. So we had to take advantage of that percent yield to figure out our expected value. Expected is what comes out of stoichiometry. Stoichiometry just relates the number of moles in a balanced chemical equation. So once we had that expected amount, I then turned it into a number of moles so I could use stoichiometry in reverse to figure out my number of moles that I would need of CuO. And once I had that number of moles of CuO, I was able to use the molar mass of CuO and find the mass of CuO that I would need to use. Okay, that's it. We're done. Chemistry 20 is finito. Well, not really. I mean, we have a couple more weeks of it. So in other words, what I want us to be doing for today is page 37 to 40 of the booklet for practice. Remember, those answers are in the back. Yesterday's lesson, which was on limiting and excess reagents, was a long one. This one wasn't nearly as long. So yesterday, you might not have been able to get to all those practice questions. So maybe you want to combine them with yesterday's too. Give them a shot. We will have a unit exam at the end of this week. And then from then on, I guess like for this year, this is 2020 right now, for this year, for January 2021, we're just going to spend those like 2 or whatever weeks of school we have just reviewing all of the concepts of Chemistry 20. Anyway, you know how to reach me. I'm in Zoom. You can email me, whatever you need, and I am there. Best of luck.